Okay, folks, number 15, almost done here. We've got 3 more for chapter 5, then you got chapter 9. So, 15 there, we've got Newton's law of cooling. Newton's law of cooling says your temperature is equal to your ambient temperature plus your starting temperature minus your ambient temperature, your current temperature, like the room temperature, e to the kt. I always liked the other form. If you subtract the c from both sides, equals t naught minus c e to the kt. Because this says the how far off we are from current temperature is going to be how far off we started times e to the kt. So this is really an amount of temperature difference equals the starting amount of temperature difference e to the kt. So this is really the same as the a equals a naught e to the kt, where amount and starting amount are amounts of change from ambient temperature. And where is this going to stop? It's going to stop as soon as this reaches 0, as soon as your change from current temperature equals 0, as you cool all the way to room temperature. So even though this formula that you're given for Newton's law of cooling looks like it's something new and different, it's really not. It is that A equals A naught e to the kt. It's just put in terms of current ambient room temperature, starting temperature, how hot the thing is now. So you can think about it whichever way you want, but it's just nice to know that this is a standard formula, and you'll use a lot in things like physics. Also, since this is modeling change, it really is our normal model, so it does apply to all those other types of applications in economics and business and sociology and all those other things. But either way, we have to be told or asked to find all of these different things. So I said we have 3 different kinds of T's. That's time, that's our constant of cooling, initial temperature, ambient temperature, environmental temperature, room temperature, however you want to say it, and current temperature, how warm it is how warm your object is at that moment. Be careful about this being current room temperature and that being current object temperature. So be careful about which one is which. C is the environmental temperature. T is the temperature of your object at a particular time t. You can actually think of this as t of t if you want to think of it as a function, but that's a lot of t's. So those are things we want. What are we told? We're told that a cup of coffee cools from a start of 120 degrees. So that's times 0 was 120 degrees. To 96 degrees, cools down to 96 degrees in 4 minutes. So that's T, 4 minutes. Outdoors at 62 degrees. At 62 degrees. Find the model T of T. Find the function, good old T of T, and use it to determine the time it'll take to cool to 74. So we want to find this function. Well, we know a lot of this function. We know the C is 62. We know T naught is 120 degrees minus 62. E to the, we don't know K, and T is our variable. So that's our function T of T. I know 4 minutes 96. We'll get there in a second. Your general model, to give the temperature at any particular time, you plug in a value for time. The problem is we have to find this K. The reason that we're given the 4 minutes and the 96 degrees is so we can calculate this K in our model. So we're told for the specific T equals 2, we end up at 96 degrees. Has to equal 62 plus 120 minus 62. E to the K, T is 4. Yeah, for that particular T. For T equals 4, you get 96. This is a very specific point on the graph. 496 is a specific point. We're using that specific point only for the purpose of finding k, so we can stick it into our model. So now solve this. Subtract the 62, subtract the 62, you get, what, 34 equals 120 minus 62 is 58. E to the k times 4. This is what I was talking about in terms of the whole, the A naught. You start out 58 degrees above the room temperature. You're now 34 degrees over the room temperature after 4 minutes. That's just A naught and A, if you want to look at it that way. Still trying to solve for k. Got to isolate the exponential, so divide off the 58. Divide off the 58. You get 17 over 29 equals e to the k times 4. Still trying to get access to that k, so we're going to put in a natural log, because that's what gives us access to exponents. So the natural log of 17/29 equals, they undo each other, k times 4, divide the 4, and k equals the natural log of 17 over 29 divided by 4. Divide by 4, divide by 4. Sorry. Those undid each other, just left us with k times 4. Then divided that 4 off. Great, so now we know our k. It might be nice to have that as a constant. Figure out, actually get a nice decimal approximation for that. Can be handy. Negative 0.1335. Carry lots of decimals. I tend to carry more decimals than that if you want to, but it's just an example. So that is our cooling constant. You can think of it as a rate of cooling. It's negative, so it's a decay. We knew it was a decay. This thing should be decaying down towards 62 degrees, getting cooler and cooler. So now we know what k is. That's the k for this model. So our model, sorry, it's getting a little messy. Our model temperature for time t is now 62 plus, we can do that subtraction, 58, e to the, we know what k is. It's negative 0.1335 t. That is now our model. So when you're asked for that model, that's what you're looking for. We were then asked to use this model to find how long it will take to cool to a certain temperature. That's essentially a separate question. Often these exponential modeling questions will have two parts. The first part, find your k, so you can build your model. Once you have your model, you can then use that model to answer whatever the question you're given is. So be sure to separate the given scenario that's allowing you to solve for k, find k, and we separate that from the question statement that says use t of t to find the time to reach, I think it's 74 degrees in this problem. Let me check. Yeah, 74 degrees. So notice we haven't used that 74 degrees at all. And we won't use the 96 and the 4 again. We use the 96 and the 4 to find k. Now that we have k, we don't need it anymore. So we want 74 degrees. That's our goal. Our model is now 62 plus 58 e to the negative 0.1335 t. That's why we had to do all that work to find k. And now we can just solve this. Subtract the 62, subtract the 62. You get what, 12? Equals 58 e to the negative 0.1335 t. Divide by 58, divide by 58. 12/58ths. Go to a decimal if you really want to, but carry lots of terms if you do. Again, we're still trying to solve for this t. How do we solve for t? That's what logarithms are for. Hopefully you're catching that theme. Log base e and exponent base e undo each other. You can see why we like using natural log, because exponent base e is so common in realistic models that, use the natural log, use the log that's going to undo them. So those go away, leaving just the negative 0.1335t divided by the negative 0.1335t, and you get t equals natural log of 12/58 over negative 0.1335. The natural log of anything less than 1 is always negative, so that's going to turn out negative by its nature. That negative will undo it, so we'll not get a nice positive time. And if you work out all the little bells and whistles in there, you should get something around 11, almost 12, 11.8 minutes. And then write your little sentence. The thing will cool to 74 degrees in 11.8 minutes. Using the model T of t equals 62 plus 58 e to the negative 0.1335t. So it's a long question. It's a big question. It's a common question. Practice these types of questions. The big key is making sure you're doing it in those two stages. Make sure you're breaking this up into the part of the question where you're using your given scenario to find k. Then the second part where you use your question value to find your answer. The number one mistake people make with these is they try to use all the values in the same model. They try to find a way to put this 74 into this part of the problem somehow, and it never works. It's not supposed to work. Keep them separate. Given scenario to find k. Once you have the k, answer your question statement. Okay, blah, 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 blah. I know. It's like I'm lecturing. Okay, 16, 2 more left. Hopefully we get them both done. I got, 8 minutes? Very similar type of question here, so I'll do it a little bit faster. Tree is measured, contains 432 board feet. 432 board feet. Of lumber in 1986. And 854 board feet in 2008. So somebody measured the height and circumference, measured the dimensions of the tree, and said, if we cut it down now, we'll be able to get 432 board feet of lumber. It's a standard measurement for lumber. How to find it, not relevant to this problem. In 2008, they measured the same tree. It's grown some. Now it's got 854 board feet in it. They want to know, find a function, and figure out, well, how long is it going to take if the growth rate continues? When is it going to be 1,000 board feet? 1,000 board feet in, they want to know, when should we schedule to come kill this tree and make lumber out of it? Well, we want to get to 1,000 board feet first. So when's it going to reach 1,000 board feet? So, like the last problem, we have a given scenario. We are given something that actually happened. Then we are asked a question. You must separate those two parts of the problem. The given scenario's job is to generate our constant, our k. The question statement, we use the k to answer. So we have to separate, just like the last one, into two pieces. One where we find k, the other where we answer our question. So for right now, we're going to ignore this 1,000. We don't care about this 1,000 right now. Now, the model we're going to use is that generic model, a equals a naught e to the kt, that model that we've really been using the whole time in different forms. And we're told with a start of 432 feet, a naught starting amount, the amount you started with was 432. It grew at some constant rate for a number of years. Well, how many years? From 2008 to 86, that's what, 14 plus 8 is 22. So it grew continuously for 22 years and reached 854 board feet. You want to get used to that being what this says. This says, hey, we started at 432 board feet. We grew continuously at an unknown rate for 22 years and ended up with 854 board feet. That's what this sentence, this mathematical sentence says. I'm going to say that one more time in a different order. We have 854 board feet, having started with 432 board feet, grown continuously, that's the E, at an unknown constant, K, for 22 years. Now, solve this for K. Divide off the 432, so 854 divided by 432 equals e to the k times 22. Yet again, how do we get to this constant that we're trying to solve? That's what logarithms are for. That's their job. And again, you could decimal approximate that if you want to, but carry lots of terms if you do, like 10 terms. Equals the natural log of e to the k times 22. And again, if you wanted to, I'll even do it here. If you want to, you can use their power property to bring that down. Certainly valid. K times 22 times the natural log of e equals the natural log of 85 over 432. But the natural log of e to what power is e to the first? This turns into a big 1. Natural log of e is just 1. So it essentially disappears, leaving you with just the k times 22. So if you want those to undo each other, leaving the k times 22, perfect. If you want to use your power property to bring it down and then simplify the natural log of e, fine. Just make sure you simplify the natural log of e. So that still equals the natural log of, I suppose we could simplify that. What, 427 over 216? 9, 10, 11, 12, 13, and I don't think that simplifies anymore, but I could be wrong. Either way, divide by your 22, divide by your 22, and we have a constant of the natural log of 427 over 216 over 22. That's your K. Sorry. Now, it really is all fine and nice to get a decimal approximation, but you want to carry as many decimals as possible. If you have learned how to store these things in your calculator, storing that value to all its decimal places in your calculator and then recalling it can be really, really helpful. If you don't know how to do that, go on YouTube and Google it. It can be a very, very, very handy technique. But this K, just for the sake of my notation here, I'm going to note it in just a couple of decimal places. But when you're doing a problem like this, you should really, you should really carry lots and lots of decimal places. The 0.031 can give you lots of inaccuracy once you put it into an exponential. So be conscious of that. Okay, I know, too much babbling. I'll try to speed up. So that gives us our model. Our model is now our amount. We're going to get an amount. We start at 432. E to the, we now know our constant. It's 0.031, positive because we're growing. T. You put in a time, and this will tell you how many board feet. You want to say A of t, probably even better. So the amount at a given time t is 434 e to the 0.031 t. This is a model for the amount of board feet given a particular time. We needed to have that given piece of information, this given scenario, to be able to find that K. Now that we have that K, we can answer any question we're asked. You want to know how many board feet we'll have in 2015? put in the value of t that associates with 2015, and we're good. Considering here that time equals 0 is, that t equals 0 is 1986. But we're specifically asked, what time do we get 1,000 board feet? So 1,000 board feet equals 432 e to the 0.031 t, and we want to solve for t. You'll notice this solving technique is going to be, we're going to look at least, really redundant. It's the same exact solving technique. You solve for t in the same way you solved for k. How do we get down this t? The same way we got down that k, with a logarithm. Put in the natural log, put in the natural log. The natural log of 500 over 216, that'll reduce more. Those undo each other, or you can use the power property like we did over there. 0.031 t. So the natural log of, what, 25, so 250 over 108, gosh, that'll still reduce, equals 0.031 t. Divide by the 0.031, divide by the 0.031. Natural log of 125 over 54. Okay, now that's not going to reduce anymore. Over 0.031 equals t, and you have an exact answer for time. Again, you can get decimal approximations along the way, but if you do, carry lots of decimal places. But this ends up being somewhere around 27 years. Add the 27 years to the 1986, and you'll get around 2012. And again, put that in a nice sentence. But hopefully this is illustrating for you fairly well the fact that it's got to be two problems. One to find your k, using your given scenario to find your k, and a separate one for your question statement. This can be kind of a time-consuming question if you're not practiced at it. These are taking me a long time because I'm trying to talk through the entire logic of them. You want to be able to do these fairly quickly. It is the same solving technique each time. So you want to make sure you're okay at doing that. Let's see, I've got one more left here. Boy, it's exactly the same type of question. So I'm just going to set that one up and let you guys play with it instead of making a whole nother video on it. But again, the model is the same. Amount at time t equals starting amount e to the kt. So starting amount grows continuously at some rate for some time, giving an ending amount. That's what this model says. So in this problem, you're told, you're given, that if you start at 3,800 and you grow continuously at some rate for 14 years, you will end up at 1,400 fish. I think it's fish. Yeah, fish. That's your given scenario. The whole 900 fish thing you don't care about until later. That's your given scenario. Solve for k. You'll divide the 38 out. You'll take the natural log. So 14 over 38. You'll take the natural log. That'll get rid of your e. You divide by the 14. That gives you k. It really is just that easy. Your k equals negative 0.99. Nope, not negative 0.99. Equals negative 0.071. About. Again, carry more decimals than that. Now that you have your constant, you now know your model. Your amount at time t equals your starting amount. 3,800 was your starting amount. E to the negative 0.071 t. This is your model for answering any questions based on this. The question you're asked, when does this equal 900? You could be given a time too and just plug in the t. Divide by the 3,800. The hundreds cancel, so 9 over 38 equals e to that power. Take the natural log, the e's go away. Divide by your k, negative 0.071 equals t. Do that longer I mean, take more time than that. Do the steps. But you'll get around, what, 20.3 years, if my notes here are correct. So it happens at somewhere around 2012. I think this one was 2013, by the way. Don't let that throw you off. So, do the steps in between there, but it's exactly like the other problem. The big thing here is to keep those 2 steps in mind. You're given scenario to find K, then use that K to answer the question. You're probably thinking, oh, you've said that so many times. People forget that every time when they do these questions. It's maddening. Don't let that happen to you. Okay. Good luck.